Assalamualaikum and hi everyone. So this is lecture 6, which is part 1 of the topic parallel programming approach. Alright, so in this topic we want to look at the programming approach which is used during the message passing. Okay, so let's look at the topic overview. First of all, we will look at the principles of message passing programming. And the next one is the building blocks of the message passings, which are send and receive operations. Number three, the MPI itself, which is the message passing interface. And the last one is collective communication operations. Okay, so let's look at the principles of message passing programming. Alright, so the logical view of a machine supporting the message passing paradigms consists of P processes, each with its own exclusive address space, which means when we deal with message passings, it needs to construct of processes, which is represented by P, and then each of these processes has their own exclusive address space. Each data element must belong to one of the partitions of the space, and the data must be explicitly partitioned and placed. So before we want to do the message passing, so we have to make sure the data has been partitioned or decomposed. Right, so all interactions, either read only or read or write, require cooperation of two processes. Either the one side is send the data or the other side is to access or to receive the data. So these two constraints, while wondrous, make underlying cause very explicit to the programmer. And actually, it's up to the programmer on how he or she wants to write the code. And then they need to consider all this situation, the number of processes, um, the sender or the receiver on how they want to receive and send the data, and what kind of operation that they need to execute, either read only or read write. So it's depend on the programmer itself. Okay, so we go to the next one. Message passing programs are often written using the asynchronous or loosely synchronous paradigms. So in the synchronous paradigm, all concurrent tasks execute asynchronously. In the loosely synchronous model, tasks or subsets of tasks synchronize to perform interactions. Between these interactions, tasks execute completely asynchronous. So it said that, so when we do the message passing program, that program actually often being written using asynchronous or loosely asynchronous. Even though it said that as loosely synchronous, only several or small number of tasks or sub-tasks that being written in synchronous paradigms. Okay, so most message passing programs are written using the single program multiple data model. We have one single program but many or multiple data. Okay. All right, so please consider this slide where how we want to build up the message passing code. So it's involves send and receive operation, where the prototypes of the operation are shown as in the slide. So we need the send and also receive method, where send and receive method consists of three arguments. Okay, so look at the send method consists of argument number one, which is the address space that stores the data, is written as void star send buff. And then number two is the number of element, which is represented as integer NLMs. And number three is to define the destination, which is the identifier of the process that receive the data. So it is represented as integer destination. So let's look at the receive. Okay, so receive also consists of three arguments, which consists of receive buffer. Number two is the number of elements, and number three is the source where to receive the from where to receive the data. Okay, so let's consider the following code segment. So which P0 and P1. As you can see, A is equals to 100 and it need to be sent to the receiver or destination. Okay, and then next one, A is being assigned to 0. However, in P1, it consists of receive methods, and then it wants to print or display the value of A. Alright, so the semantics of the send operation require that the value received by the process P1 must be 100 as opposed to 0. So this motivates the design of the send and receive protocol. So we have to make sure the receiver must receive 100 instead of 0. So the programmer need to verify or to plan on how to send and receive at the correct time and location or in required period. Okay, so next one. So another approach that the programmer need to be considered is called as non-buffered blocking message passing operation. So it is another one approach where a simple method for forcing send or receive semantics is for the send operation to only return when it is safe to do so. So this is a non-buffered blocking operation. So in the non-buffered blocking send, the operation does not return until the matching receive has been encountered at the receiving process. So the sender need to wait, okay, and then cannot return to its place until it find the match, okay, at the receive place has been encountered. Okay, so due to this, idling and deadlocks might be occurred with the if we implement the non-buffered blocking send process. So in buffered blocking send, the sender simply copies the data into the designated buffer and returns after the copy operation has been completed. So the data is copied at the buffer at the receiving end as well. So this approach, which is buffered blocking send, is being implemented to overcome the issue of idling and deadlock when we implement with unbuffered blocking. So the buffering actually alleviates or reduces the idling time at the expense of copying overhead. So even though we can alleviate or reduce the idling, but it might increase the copying overhead because we need to copy the data to the buffer. Okay. Alright, so next one, this is the illustration of the implementation non-buffered blocking approach. As you can see at A, alright, so A, the sender comes first and then there is an idling situation at the sender. So as you can see here, the sender send a request to send to the receiver. However, the receiver is not available at that time. So the sender need to wait for a while until the receiver free and send the message okay to the sender. So this is the time or the period where the data is being sent from sender to the receiver. Okay, so compared to B, B is the situation where the sender and receiver come about at the same time. So this situation actually might reduce the ID. Of course, it can reduce the ID whereby the sender no need to wait for the receiver to receive or to send the data. So it happen at the same time. So there is no idling issue compared to A where sender has an idling issue. Okay, how about C? Okay, C, the receiver comes first and the idling still happen where during this time the receiver is free to receive any data but the sender is not available to send the data. So during the time of the waiting time of the sender to send the data, okay, it's will issue the idling situation. So when it's send okay the message to the sender, then the sender can send the data to the receiver. So this is how the non-buffered blocking be implemented. Basically, there are three situations might happen. All right. Okay, next. This one is the buffered blocking message passing operation. So as we discussed in the previous slide, when we implement buffered, actually it will reduce the idling and deadlocking problem. Okay. However, it's really rely on the buffers at the sending and also the receiving ends. So the sender simply copies the data into the designed buffer and returns after the copy operation has been completed. So the data must be buffered at the receiving end as well. So not only copy at the buffer, the sender, but also at the receiver. When we implement buffered, it's really reduce the idling of head. However, it might increase the buffer copying over head. Okay. So next, this is the illustration between this is an A diagram and this one is B. So in A, the presence of the communication hardware with buffers at send and receive ends. So this diagram at the left side implement hardware communication. There is an interaction between the sender and also the receiver. Okay, so B, there is no communication hardware being implemented. The sender interrupts receiver during the execution of the process and deposit the data in the buffer at receiver. And okay, in A, there is no communication between sender and receiver. The sender just send the data with the communication hardware. Means it do some interaction between the sender and also the receiver before it send the data. Okay, so in B, all right, the sender send the data without tell the receiver that it wants to send the data. It just copy the data into the buffer. So at that time, the data copied to buffer at the receiver and then actually it's interrupt the receiver and then the data will be executed or deposit in buffer at the receiver end. Okay, right, next. So this is an example of buffered blocking. So bounded buffer sizes can have significant impact on performance. So if we implement buffered blocking, actually it also has a limitation on the sizes. So when we want to use the buffer blocking, actually we can set or bound the buffer sizes. So in this example, it bound the buffer size into 1000. Okay, all right. So this is the example between buffer and sizes of the sender and also this one is the receiver. Okay, where we can see here the buffer, the bounded buffer is equal equals to 1,000. However, we need to consider this kind of question. What if consumer was much slower than producer? So what we need to do? Okay, so you need to think uh, what should be, what happened if the consumer was much slower than producer. As for the time being, we know that usually the receiver is uh, ready or faster, okay, than the producer or the sender. Okay, but this time the consumer or the receiver is much slower than producer. Okay. All right. So next, buffer blocking message passing operation. This is the deadlock situation. So deadlocks are still possible with buffering since receive operations block. So it said that between P0 and P1, both P0 and P1 implement the same operation, which are receive at P0 and P1 is also received using the receive function. And then at the second line, P0 send the data and the P1 also send the data. Okay, this kind of operation is called as deadlock. Why deadlock? All the operations are the same within P0 and also P1. So it might generate the deadlock. Okay. Right. So next one, non-blocking message passing operation. The programmer must ensure semantics of the send and receive. Yes, the programmer need to know, need to analyze and look deeper or in detail. Okay. Uh, what is all about the message passing operation between send and receive. So this one is this class of non-blocking protocols returns from the send and receive operation before it is semantically safe to do. So if we implement non-blocking protocols, so we need to check, make sure whereby the data is safe to be stored or write or not. So non-block to make sure this non-blocking operations use check status operation. So when this operation is being used correctly, these primitives are capable of overlapping communication overhead with, with useful computation. Sorry. Message passing in libraries typically provide both blocking and non-blocking primitive. So not only non-blocking primitive or approach can be implemented in message passing, blocking message passing also can be implemented. Okay. Let's look at the diagram. So in A, the non-blocking message passing without using hardware support. So the difference is at the sending data process, whereby in A, okay, in absence of communication hardware, when the sender wants to send the data, all right, it is unsafe to update data being sent because it's not implement any hardware to tell the sender or receiver the current situation. And B, with the implementation of the hardware, suppose we know that actually it is also unsafe to update data being set, but actually it's quite safer when we implement non-blocking with hardware support, whereby we know or we can check the status of the data either being stored or not into the buffer, either being safe during the sending process or not. Okay, next one. So this is the summarization of the approach that we have discussed before between send and receive protocols, okay, between buffered and blocking, buffered non-blocking, non-buffered and blocking operation. So the main point is when we implement buffered and blocking operation, the sending process returns after data has been copied into the communication buffer, and between buffered and non-blocking, sending process returns after initiating DMA transfer to buffer, and this operation may not be completed on return. So that's why we can see in previous slide, it notify that the data that we copied or sent might not be safe, may or may not be completed during the return. So if we implement non-buffered and blocking operation, so the sending process blocks until matching receive operation has been encountered. So as you can see here, if we implement non-buffered, maybe the idling and also the deadlock might happen. Okay. Actually, it's all about the programmer on what kind of approach or paradigms that they want to use during the message passing code writing process. Okay, so space of possible protocols for send and receive operation. Okay, so next one. So what is meant by MPI? So MPI is the message passing interface. So MPI defines a standard library for message passing that can be used to develop portable message passing using either C or Fortran. So we need to implement this kind of library to send the message or to do the message passing operation. Okay, so the MPI standard defines both the syntax as well as the semantics of a core set of library routine. So vendor implementation of MPI are available on almost all commercial parallel computers, and it is possible to write fully functional message passing programs by using only the 6 routine. So actually, the MPI has the routines that need to be followed during the code writing using MPI. Okay, so these are the routines: MPI init, finalize, concise, combrand, send, and receive. So these are the functions, okay, for each of the routines. Init is to initializes the MPI. Finalize to terminate the MPI. Concise to determines the number of processes. Combrand determines the level of calling processes. Send sends a message. Receives a message. Okay. Okay. So how to start and terminate the MPI library? This is the code. Okay. To start is by using MPI init to initialize the MPI environment, and to stop or to terminate the MPI, so we need to use the finalize. Okay, this is the prototype of these two functions that can be used in the code. Okay. What else? So the communicators. So communicators defines a communication domain, which is a set of processes that are allowed to communicate with each other. So we need to use the keyword MPI or the routine MPI underscore com. So communicators are used as arguments to all message transfer MPI routine. So a process can belong to many different, possibly overlapping communication domains. Okay, so this is the default communicator MPI com underscore were, which includes all the processes. Okay, so querying information. So to query or to know, to determine the number of processes and the level of the calling processes. So we can implement this one, MPI com size and MPI com rank with the respective arguments. So the rank of a process is an integer, okay, that ranges from 0 up to the size of the communicator minus 1. So you can define. So what is the size and also the rank of the communicator of the process size. Okay. Okay. So as you can see here at the slide is the first MPI program which is written in C. So include MPIH and then with the main method here, okay, that implement init, comsize, comrank and finalize. And then in this program, it wants to display uh, the process of processor D out of how many from how many to how many, then it will print the hello world message and then display also the rank and also number of process. Okay, all right. So sending and receiving messages. The basic function for sending and receiving messages in MPI are using MPI send and MPI receive. So this is the prototype or the syntax that we may use to send and receive the data. Okay, so the data type can be either byte or tag. Okay, the message tag. Okay, this is the syntax for message tag. Okay, what else? So these are the data types that can be used during the data assigning or assignment. Okay, and then sending and receiving messages. The MPI allows specification of wildcard arguments for both source and tag. So if you implement MPI any source, then any process of the communication domain can be source of the message. And if you implement MPI any tag, then messages with any tag are accepted, right? So there are many uh, tag that can be implemented. Okay, this is the MPI receive operation. Okay, and other functions. Okay, ni. This one is the example to avoid the deadlocks. In this case, this code implement two sending operation and then two receive operations. So we can see here there is a deadlock happen here where all the processor wants to send at the same time and this one want to receive at the same time. So when MPI send both destination A and B or 1 to 2, okay, it might be a deadlock. So actually it's a deadlock because there is no processor that wants to receive the data, right? So how to avoid the deadlock? So we need to change to alter a little bit on the program code whereby it need to be alternate between send and receive. So we first send the data and then followed by the receive process. Alright. So this is another example. We also can break the circular wait to avoid the deadlocks. Okay. In this case, just now we can see here both programs are send operation. And just right now we are change the operation starting from send to receive and this one is receive and sending. Okay, as long as not from the same operation, so we can avoid the deadlocks. Okay. So sending and receiving to exchange messages, MPI provides the following function. So this is the example to exchange the messages. Right? And then collective communication and computation operation. So MPI provides an extensive sets of function for performing common collective communication operation. Okay, all processes in a communicator must call this operation. Right. So what are the communicator or the communication operation? So there are such as MPI barrier, broadcast, MPI reduce, okay, and many more. So these are some of the example that can be implemented in the message passing operation. Okay, so that's all for this chapter. So we continue this topic in the next lecture 7. Thank you all.